get it started on my end as well. All right. Welcome, ladies and gentlemen, to our virtual New Vistas for tonight. Couple of brief announcements. The next New Vistas talk, the last of the series for this year, will be on December 10th at 8 p.m. as usual, and it'll be given by our own Dr. Robert Harmon from Ohio Wesleyan, discussing, we're talking about stellar heartbeats. And if you've attended these before, you know Bob, Dr. Harmon is a good speaker and should be an enjoyable talk. We're continuing the virtual Friday night programs as well. Tomorrow night being one of them. Looks like it's so far forecasting to be a nice night, and hopefully we'll be able to do some virtual telescope observing with the telescopes at the observatory. Last week had some weird internet problems. Hopefully that won't be the case this time around. But that'll start also at 8 p.m. Tomorrow night. Like I said, hopefully I'll be doing it from Perkins and doing, again, with some telescopes. So we got Jupiter and Saturn and Mars in the sky. And so there's plenty of things to see through the telescope, and it worked out pretty well in the past when I've not had technical difficulty. So hopefully this time around it'll go smoothly. Without further ado, it's my pleasure to introduce tonight's speaker, Dr. Michael Stamatikos from Ohio State, just talking about a beautiful fluctuation, entropy, and the arrow of time. Take it away.
All right. Thank you, Don. And thank you all for joining me this evening to discuss a topic I've been thinking about for a while and wanted to pull a couple ideas together and share them with you. If anything is interesting and you want to continue the conversation, I leave my email here on the bottom, stamatikos.1@osu.edu. I'm happy to continue the conversation. And we're recording this Zoom session tonight, and I'm sure it'll be posted somewhere so you can get your hands on it as well. So thank you all for having me. You guys are a great crowd. I do this usually every year. So the thing I want to discuss really is what is time, and in particular, more specifically, why time has an arrow. Why do we not remember the future, essentially is another way of saying it. And one of the classical starting points is Confessions by St. Augustine. In particular, book 11, chapter 14, he's famously quoted as saying, "What then is time? If no one asks me, I know. If I wish to explain to him who asks, I know not." And this is a real common experience. I mean, if you're in your daily life, time is important and you have certain meanings ascribed to it. But when you really want to break it down, it's almost hard to define itself without using time in the definition. So of course, I turn to the keeper of all knowledge, Wikipedia. And if we go there, we see that time is an indefinite continued progress of existence and events that occur in an apparently irreversible succession from the past through the present into the future. And I underlined parts of that definition that I'm going to be addressing. The indefinite part, the fact that it's irreversible, and this seemingly, category of past, present, and future. And then for good measure, I also looked at the Merriam-Webster site, and their definition is the measured or measurable period during which an action, process, or condition exists or continues. And then the second one is a non-spatial continuum that is measured in terms of events which succeed one another from past through present to future. So key to these things is some kind of periodicity that we can ascribe to keep time in some unit of measure. So what I want to first look at is one of the earliest timekeeping mechanisms that we had was essentially looking up at the heavens. And what you're looking at here is a northern view of the sky. This is around 2 in the morning tomorrow, actually 2 in the morning in a few hours. And is the screen share still working? I'm getting a message here that the screen share stopped.
Yeah, it stopped for some reason. It just dropped.
Okay, let me try that again. Is that working?
Yeah, there we go.
Okay, so you're looking at a northern view in a few hours here. The North Star is there, and we have a couple of things that I want to discuss. One of them is this galaxy NGC 3972, which I'll discuss more about, and then another galaxy, the World Galaxy M51. And there's this stately progression that we see when we look up into the heavens, and we're able to, in this case, lock in on the North Star. Our rotation axis is co-aligned, and then everything seems to be rotating in a stately manner around that point. So this is something that, the sun, the moon, planets, the stars followed these kinds of periodicity, and this was the first way that we tried to connect with time. The interesting thing is, for a long time, we thought that we were the center of everything, right? So we know now, of course, through the heliocentric model, that in fact it isn't the celestial sphere that is moving around us, it's the other way around. And we actually get this kind of counterclockwise rotation. And this is what simulates the sky rotating above us. And we've known that since the heliocentric days. But the laws of physics that govern which direction the rotation is time reversible. So we have here, for example, the Earth rotating counterclockwise, but I can show you, for example, Venus. And Venus is rotating in the clockwise direction. Same thing happens for Uranus. We play that forward. And here I'm speeding up the rotation, but you see it's a clockwise rotation as you view from the northern hemisphere. So the direction of motion will depend on the actual microphysics that went into creating that body. But we see that even within our solar system, the planets don't always rotate in the same direction. Same thing holds true with any other body that I wish to discuss. Here we're looking at the asteroid belt, and we have the inner planets and of course the sun at the center. If I run this forward, everything is orbiting. Now we're not looking at the rotation per se of each planet, we're looking at just the orbit. And everything certainly is orbiting in a kind of counterclockwise way. However, if I run this in reverse, and I never told you what solar system this was, the laws of physics would still apply. And in this sense, on a kind of fundamental level, the laws of physics are time reversible. So there's nothing in the laws of physics that choose a particular time direction or an arrow to time. And that's something I want you to think about as we continue. So I got out of that program. Hopefully my next slide is visible. Is that true? Time, fundamental quantity of mechanics?
Not seeing it yet.
Not seeing it yet. Okay. For some reason, Zoom is not behaving as normal. So let's see if I do this again. Hold on. How about that? Did that work?
Yes, there we go.
Okay, fundamental quantity of mechanics. Okay, so by fundamental quantity, what we're really talking about is we can't break time down into a simpler measure or a simpler thing. Same thing is true for length, and we'll talk about that momentarily. But because we are reliant on the sun, and the ancients were amused by the motion of the celestial bodies, that was the first underpinning of how we would measure time. In fact, it would be the average solar day, and one solar day would be 86,400 seconds. And then eventually we ended up getting into realizing that, of course, if you want high precision in the definition of time, you don't look at necessarily planets and moons and things, because you have changes. You have mutations and permutations over time. So then what happened is they averaged it to the tropical year 1900. Eventually, in the late 60s, we went to atomic clocks. And to this day, we're using cesium clocks. In fact, the change between the two hyperfine levels that are oscillating at over 9.1 billion times. And this is what has stabilized the definition of the second. So the precision going from early mechanical clocks, you're looking at losing anywhere from 15 minutes to 1 minute per day. If you start going into advanced mechanical clocks, even the quartz clock and things like this, you're still losing about a second per day, but you're approaching a second per 1,000 years. And the atomic clocks that we have today, in fact, in the beginning of 2013, the uncertainty was reduced to the point where you would neither gain or lose a second within 100 million years. And of course, now with optical clocks, we're pushing precision to 1 second per 10 billion years. So I don't know what kind of wristwatch you own, but this is incredible precision that you would want if you're making kinds of measurements. Well, can we go down indefinitely? How small of a time measure can we get? And this actually was done recently. It's around 250 zeptoseconds. This is a laboratory measurement. This is the smallest unit of time observed in a laboratory. And a zeptosecond is a trillionth of a billionth of a second. It's 10 to the minus 21. And essentially what they did is they measured the time it would take a photon, that's shown here in yellow, to cross a hydrogen molecule. So that's about 250 zeptoseconds. The only thing smaller than that will be a yoctosecond, 10 to the minus 24, and then also Planck time, which is our fundamental limit. And of course, here you have to go back to the metric system. The US doesn't really use it yet, maybe never will. But if you look at the base 10 parameterization, we're into the negative 21, 10 to the negative 21. That's the zepto. Now, once you get the definition of a second, the next thing that's very fundamental would be the speed of light. And the speed of light is something that comes out naturally from fundamental units. And this is brought to you by James Maxwell. James Maxwell's equations, unified electricity and magnetism. He did for electricity and magnetism what Newton did for mechanics. And just as Newton benefited from Galileo, Einstein benefited greatly from Maxwell. In Maxwell's equations, there's a defined wave speed of the electromagnetic pulses. And from the constants of nature, that comes out to a very specific number, roughly 3 times 10 to the 8th meters per second. And what Einstein wanted to do was to elevate Maxwell's equations to the same pantheon as Newton's equations, under the umbrella of fundamental physics. So if all fundamental physics, if all the laws of physics are the same in all reference frames, inertial reference frames, then he wanted to be able to include that. So in order to do that, it required all observers to measure the speed of light at exactly this, which I'm going to round to 3 times 10 to the 8th meters per second. It's about 700 million miles per hour. Now, once you label that as your fundamental speed, you can then define a meter as 1 over the time that it would take to travel that distance, a photon to travel that distance. So there's this connection between the fundamental time and the fundamental length that we can get. Now, if you look at the other theories that we'll discuss, general relativity, quantum mechanics, special relativity, they also have their own sets of constants. And Max Planck realized that he could play with these constants in a dimensional way to come out with very fundamental measures for, in this case, time and length. You can also do it for mass, but I'm going to be focusing on time mostly and a little bit of length. So when you look at those fundamental constants, the Planck time is something like 10 to the minus 43, so much smaller than 10 to the minus 21. And the Planck length is something like 10 to the minus 35 meters. Now, to understand what this means, these are the smallest units of both time and space that I can use and still have the laws of physics make sense. time is not well defined in intervals smaller than 10 to the minus 43, neither is space in intervals of 10 to the minus 35 meters. So in some sense, you can think of space-time as being pixelated on these fundamental scales. And this is why when you see diagrams that trace back, let's say, temperatures and times and forces, there's this cutoff that you see at around 10 to the minus 43 seconds. And that's that fundamental roadblock that we get. It has nothing to do with precision or how well we can build an atomic clock. That's built in from nature. So the big problem we have today is trying to reconcile all the theories that are very successful independently, but can't seem to be combined into a theory of everything. And here I'm looking at quantum physics, general relativity, and special relativity. And Einstein had a lot to do with all of these. Now, if you're much larger than an atom and you're moving much slower than a photon, then classical mechanics, the world of Newton's Principia, would be fine for you. But the faster you go with respect to the speed of light, you have to make corrections for special relativity. And we're actually going to do some of those. If you get smaller, you have to make corrections for quantum mechanics. And if you get smaller and move fast, you have to go into quantum field theory. But before we get into Einstein's special theory relativity, I want to go through an exercise with you that's considered more of a classical or Galilean relativity. And what I want you to consider is having an individual in the back of the bed of a truck here throw a ball completely vertically upwards. And what they would see is the ball would move up, slow down, stop, and come back down again. Now that would be the case if the truck were stationary with respect to the ground. And it would also be the case if the truck were moving at a constant velocity. And by constant velocity, I mean same speed, same direction. So as long as the speed and direction didn't change, the hand of the individual who threw the ball up will always be directly underneath the ball, and they would see the trajectory of this ball being simply straight up and down. If you then say, well, what if you have a different point of view? What if instead of looking at the up and down motion from the car itself, what if you had the car moving and then someone outside at rest with respect to the sidewalk was looking at this? Well, what they would see would be a parabola. They would see the simultaneous motion of the ball being thrown upward. That component comes from the person that's throwing the ball up, but they would also see a component that's going to the right due to the motion of the truck. And a velocity up and a velocity to the right as a vector adds as kind of a velocity at an angle. And this person would see a trajectory that is consistent with a parabola. So the question I have for you is, what is the real trajectory of the ball? Any guesses? Well, you might be tempted. Go ahead.
I said type it in chat.
Yeah, I'm trying to get my chat also disappeared for some reason. Let me see if I can. Okay, I got my chat up now. Okay, so I also have participants up as well. Very good. All right. So the short answer here is that there is no special inertial reference frame. In both cases, the observers are not accelerating. So in this individual, they're at rest and they remain at rest. This individual moves at a constant speed in a constant direction. That means you can't ascribe a special frame of reference if they're both inertial. So the reality is the person in the truck sees a real trajectory up and down. The person in the sidewalk sees a real trajectory as a parabola. What they would agree on is how long the ball stayed in the air. And if they both made measurements, the seconds, if they both had a stopwatch and they synchronized it, each second that ticked on the sidewalk watch would also be the same interval that's being ticked in the person in the truck. And that's nothing to do with Einstein. That's Galilean relativity, understanding that there's no preferred inertial reference frame. Another way you can think about it is if you have a train that's moving at 9 meters per second with respect to the ground, and then you have someone walking in the train and they're moving 2 meters per second with respect to the train. And the question is, what is the velocity of the person? Now, to someone outside here, they would have to measure the speed of the train and add it to the speed of the person. And they would say that they're traveling at 11 meters per second with respect to this person on the ground. So depending on who is doing the observation, you're going to get different values. And this comes from the fact that length and time are no longer, they're no longer universal. They are in fact personal to the inertial reference frame that's making it. So there's no such thing as absolute length, no such thing as absolute time. And this is how you can get the laws of physics to be the same in all reference frames, because we want to get the speed of light the same by all observers. So I want to go through a derivation here. In years past, I found your audience to be better prepared than most audiences. So this is also will be recorded, so you can go back and look at this derivation. But I wanted to do a similar thought experiment, but instead of throwing a ball up in the air, what I'm going to do is I'm going to shoot a photon. And I'm going to have a flashlight. I'm going to shoot a photon up. It'll reflect off a mirror and come back down again. And I can talk about the path of the photon and how long it takes to make that distance. So again, there'll be two frames of reference. One frame of reference will be the person in the train at this point, and they are at rest with respect to the train. And then there'll be a person that's outside. And in a similar way, the person inside just sees a vertical path up and down. However, the person outside, because the train is moving, would actually see a longer path that the photon would have to travel to bounce off that mirror and come back down again to this detector. Okay, so we can compare these two paths. Now here, what we need to get into is this idea of proper time. And proper time is going to be the interval that's going to be measured by a person who sees the events occur at the same point in space. Okay, so the proper time here is going to be measured by the individual on the train. And if you use freshman physics, and this is actually a derivation we do with our 1250 students that are scientists and engineer majors, if you use this equation and realize that light is constant, so there's no acceleration, and the distance is simply twice d, in this case, if it goes up and down, you can get a relationship for how long that time would take, given the distance, 2d, and the speed. Right? Divide the distance by the speed, you get the time. And I'm going to define something here that's going to be useful later. I'm going to define d squared, and that's going to be the square of c times the proper time divided by 2. And that's how you would analyze that if you were in the train itself. Now, if you are outside and looking in, it gets a little bit more complicated, but not much. All of this is really algebra and a little bit of trig, maybe a little bit of geometry as well. But you can imagine this path being a part of this triangle, and you can define what that is. And through the Pythagorean theorem, you can come up with a relationship of how you can connect that d squared value. In this case, it's not a straight up and down motion. You have to worry about this hypotenuse. And if you work through those details, and all the details are here, and of course you can go back and look at them, what you end up coming up with is a relationship between the time that's measured by the person that's outside the train and the proper time that's measured by the person inside the train. And that relationship is the Lorentz factor, the gamma factor that is the calling card of special relativity. Anytime you see a gamma factor, you know that special relativity is important to that equation. Now notice the denominator here. If v is very small, c we know is very big, it's 700 million miles per hour, so c squared is a very large number. If v is very small compared to c, then essentially this fraction is 0. And 1 minus 0 is 1, and the square root of 1 is 1, and 1 over 1 is 1. So gamma is either going to be 1 or greater. And if gamma is 1, you're essentially in the classical regime. Now, gamma doesn't really start to take effect until you approach the speed of light. So as you see here on the x-axis, we have velocity in units of 10 to the 8 meters per second. So 3 times 10 to the 8 meters per second, this vertical line represents the speed of light. And as you approach the speed of light, your gamma factor goes up exponentially. But even if you're traveling at 700,000 miles per hour, your timing differences would be something like 5 parts in 10 to the 7th. So you simply don't have any experience doing this. You're in a car, you're going 60 miles an hour. Even if you're in a race car, you're going only 200 miles an hour. If you ramp up on a plane or the Earth's equator, or even if you look at the Virgo supercluster, you're still at just 1 million miles per hour. Light is going at 700 million miles per hour. So in our everyday life, we don't have to make special relativistic corrections. But these are real, and these have been observed since the 70s using aircraft that are moving at speeds that are different than terrestrial atomic clocks that were calibrated before the aircraft took off. So here you see the differences are in nanoseconds. So nano is a billionth of a second, and we have predicted differences and measured differences. And the sign shifting here is because you go east in one way and you go west in the other way, and that will change the difference in the sign between the clock on the aircraft versus the clock in the laboratory. And this also happens every day when you use GPS. GPS corrections require the clocks on the GPS satellites to be in agreement with the GPS receivers, and that accuracy needs to be about 25 nanoseconds. So within 25 billionths of a second, that's your threshold for precision to get good GPS localization. Because of this special relativistic effect, it introduces an error of the order of 7 microseconds. There's another effect that's greater due to general relativity, and that's nearly 50 microseconds. So the upshot between those two effects is roughly 40 microseconds. But you might say, well, that's 40 millionths of a second. Why would I need that precision? Well, I just told you that you need 25 billionths of a second agreement. So a billionth and a million, that's a factor of 1,000. So you're beyond the threshold by a factor of 1,000. If you didn't correct this, then within 2 minutes, you're going to be in error, and you're going to accrue an error at about 10 kilometers per day. So these are very real corrections that happen in particle accelerators, that happen on your dashboard, in your cell phone. This is real physics that affects your life. I'll spare you the derivation for the length contraction, but you can do a similar thought experiment where instead of shooting the photon up and down, you shoot it left and right. And what that leads to is another Lorentz correction, and in this case, there's a contraction. So lengths get contracted, times get increased, depending on which reference frame you're looking at. It's about the relative motion. And no one clock is more accurate than the other. It depends on what your frame of reference is. So what I want to do is give you another real example of how this works. And I want to consider the case of atmospheric muons. So for over 100 years, we've known that we have cosmic rays coming in from space, interacting with our atmosphere, similar to particle accelerators crashing particles together. And in that crashing of the particles, 3 equals mc squared, you get other particles that may or may not survive given their half-life as they reach down to the ground. And one of these particles is a muon. Now, if you make a muon in the lab and you're at rest with the muon, it will live for about 2 millionths of a second. Its half-life is 2 times 10 to the 6 seconds. And these muons are born in interactions that are kilometers high into the atmosphere. So when you look at their half-life and you look at the distance they have to travel, you can estimate from a classical point of view that essentially none will make it. About 0.3 out of a million should make it to the surface if we are in the world of Newton. The problem is when you do this experiment, nearly all the muons make it to the ground. And the interesting thing that occurs here is you have to ask the question, who's measuring the distance and who's measuring the time? So if we look at it, for example, from the muons reference frame, the muons reference frame would measure itself as having that lab frame of 2 microseconds. However, if you're looking at the muon, if you're looking at the Earth frame, they're not measuring the muon frame, they're measuring the point at the very top and the point at the bottom, and what they end up getting is a stretched time dilated effect. Okay, so they end up living for around 16 microseconds. And that 16 microseconds accounts for the fact that they traversed nearly 5,000 meters in this case. In the case of the muon frame, it would think it only lives for 2 microseconds, but it would think that it only traveled about 700 meters. So it sees a contracted length living the proper time of 2 microseconds, and the scientists measure a time dilation in the decay rate, allowing them to live. Now the question is, which length and which time is correct? Did they really live for 2 microseconds, or did they live for 16 microseconds? Did they really travel 650 meters, or did they really travel 4,700 meters? And the answer is, depending on the frame, those answers will change. The reality that we're grounded in is that the muons made it. So both frames of reference would agree the muons made it to the ground. However, they would disagree on the time it took and the distance they traveled. Now, if you continue this, and if you build mechanics from distance and speed and velocities, and then you build energy arguments, and then you build momentum arguments, all these changes have cascading effects. And what you end up doing is, when you look at coordinate systems and how coordinate systems translate when there's relative motion, when you run through those calculations, incorporating the dilation effects, you end up getting this conflation between time and space. And I'm circling it here with my cursor, okay? I have time here in the primed moving frame is related to time in the stationary frame that you would expect. There's a gamma factor you expect. The U there is the relative speed, the speed of light, and then X. So in this equation, you actually see the conflation of space and time. They cannot be separated. So it's not a poetic term when physicists say we have space-time. Space-time is an entangled thing that is the arena of our reality that combines space and time in a very intimate way, and that comes directly from special relativity. If you were to further take these corrections into kinetic energy, you would derive E equals mc squared. So the mass equivalence and space-time come directly from special relativity, and that comes from this idea of Einstein wanting to keep Maxwell's equation the same for all inertial observers. So you can get into general relativity, where you look at Einstein's theory of gravity, but when you look at that too, you still have this conflation of space-time and space-time intervals. So you can't escape this time factor being conflated with space. If you go down to quantum mechanics, you also see the wave functions having a temporal component. But here's the thing, all the equations that I've shown you on this fundamental level do not prefer a direction. They don't give a direction to time. They are reversible. So the antiparticle and the particle can meet, annihilate, and give off energy, photons, and the reverse can happen. Just the same way you can have planets orbiting in different directions. So there's nothing baked in to the fundamental laws of physics that give it a direction. So that's one thing I want to underscore. The next thing I want to underscore is this illusion of now. And this is something that bothered Einstein. He said that the distinction between the past, present, and future is only a stubbornly persistent illusion. And there's various ways of thinking about this. One simple, straightforward way is to realize, since the speed of light is finite, it takes time for light to travel given distance. So if we're looking at the time it takes for light to travel from the moon to the Earth, then that takes just over a second, 1.29 light seconds. It takes about 8 minutes and 19 seconds for light to escape the surface of the sun. And our closest star is over 4 light years away. And our galaxy is about 100,000 light years across. So by definition, anytime you see something, you're seeing it in the past. And that past time is simply the time it would need for that speed of light to reach you, traveling at the speed of light over that distance. So in this way, we are kind of prisoners of time, and we have this direction that we don't find on a fundamental level, but emerges when we look at macroscopic systems. And one example I want to give you is looking at this galaxy here. This galaxy is NGC 3972, and this is at a distance that's roughly 65 million light years away from Earth. This was one of the galaxies that I pointed out in the earlier portion of my talk. And the reason why I point this out is, from the Kepler satellite, we know that most stars have planets. And there potentially could be a planet orbiting a star in this 100 billion star system that has intelligent life and maybe has built telescopes. And if they had a super telescope that would look at the Milky Way galaxy right now in their reference frame, they would see not humans, they would actually see dinosaurs. So there now is our past. So when is now? There's nothing special about now. If you look at the equations, there's nothing that specializes now, nothing that specializes past, present, or future. It is an emergent illusion that comes from macroscopic thermodynamics. So now we get to The Persistence of Memory by Salvatore Dali, right? And maybe you feel like this now, these melting clocks after this discussion. But another way of asking this is saying, why don't we remember the future? That really underscores the arrow of time. And for this, we have to bring in a wonderful thermodynamic idea proposed by Boltzmann called entropy. And the first law of thermodynamics essentially is a conservation of energy statement. The second law of thermodynamics tells you the arrow of time. This is the idea of entropy and the fact that entropy increases. Now, entropy is loosely a measure of the disorder of a system. And I'm going to run through several examples to give you some sense of what we're talking about. The first example is a deck of cards. On the left-hand side here, you see that the cards are all ordered in increasing value for each given suit. So this is a highly ordered system. However, if you were to leave these cards out on a table and maybe bring in some kindergartners and they were playing with everything in the room and they left, it would probably look something like what's on the right-hand side. Now, this is a highly disordered system. Now, this is a special state on the left. There's only one way that I can arrange these cards in this manner. However, imagine the number of ways that I can mix them up and they still would be mixed up, if you will. So this is pointing to this idea that there's a macro state of order and there's a macro state of disorder, but there are many more micro states of getting disorder than there are order. So saying that entropy increases, going from this ordered card deck to the disordered card deck, is this arrow of time. You would expect that this to occur naturally over time. It takes work and effort to go the other direction. Someone had to actually physically put those cards in order. Maybe a more, maybe an example that hits closer to home is the idea of a messy room or a messy desk. Now, imagine this room was very organized before this picture was taken, and everything had a very specific place, okay? That's a highly ordered system. However, as time goes on, entropy takes over and things get disordered. But imagine, what if I took this skateboard and I moved it over here and took this shoe and put it where the skateboard was? It would still look messy. And I can permute all those different things and it would still look like a messy room. So there's many, many ways I can make this room messy. There's only one or two ways I can make it how I want, highly ordered. So over time, you expect this to occur. So let me give you an example that hopefully drives it home. So you go to the beach and you look at a perfectly flat sand, right? So it's nicely flat sand. And this is a macro state of the beach, right? This is what the beach looks like. But you know that the sand is made of particles, right? There's grains of sand that you can take out and put in. So this is an ensemble of microstates. It's an ensemble of microstates of where these sand particles, where these grains of sand are. So if you were to go to the beach and you were to say, look, I have a lot of time on my hands, let me do an experiment. Let me take 2 points on the beach, and you see it here in these red circles. And what I'm going to do, I'm going to magnify those. So I have grains of sand in this area. I have grains of sand in that area. And what I'm going to do is I'm going to select a single grain of sand from this spot. There it is. And I'm going to select another single grain of sand from this spot. There that is. And now what I'm going to do is I'm going to swap them. Right? So the grain of sand that was here is now going to be put over here, and the grain of sand that was there is going to be put over there. And then when I step back, I still see this. And I'll spare you the permutations. I can do that with every single pair of sand, and it would still look like this. So there are many, many different ways that I can get the beach to look flat. And this is why the expectation over time is that any ordered system would evolve to this highly disordered state where you have randomized all the positions. Now, with sand, an ordered system would be a sandcastle. So you're building a sandcastle. If you build a sandcastle, now you have a highly ordered subset of sand particles that are highly ordered with respect to the rest of the sand on the beach. You can do the same game of swapping grains of sand in the volume of the sandcastle. However, if you consider the set of sand particles in the sandcastle versus the global set that you see on the beach, you run into this issue. Now, if you were to look at a video, and a video hopefully should be coming up now. And in this video, you see a sandcastle. And what we're going to do is we're going to let time go forward. And of course, what you would expect is this sandcastle is probably not going to last the test of time. There's going to be wind. There's going to be tides. And you see a tide coming in here. Intoxicated seagulls could crash into it. Disgruntled teenagers could kick it. And as you see here, the highly ordered state of the sandcastle is being destroyed into a highly disordered state that we're going to get eventually this to be flattened out. If you see this movie in this direction, you have no problem with seeing it other than the tender feelings for losing the sandcastle. But if I were to show you this video in reverse, if I were to show you a tide coming in and then sculpting this sandcastle and effectively having the sandcastle arise from the background of sand, you would be troubled by that. That's a time reversal that you've never seen before. But what I want to tell you is that there is nothing in the laws of physics that prohibit that other than the sheer statistical low probability of that occurring. So the fact that we see the sandcastle decay in the background and not the reverse is that it's so highly improbable for the reverse to happen. So in this sense, we can get a direction to time through this idea of entropy, this idea of microstates. So you start off with a highly ordered system, and then you go into disorder. And you can use this to talk about thermodynamics. You can use this to talk about a psychological era of time, and actually the cosmological era of time that we have started since 13.7 billion years at the Big Bang event. Now, how do we get from the macroscopic to the microscopic? Well, there was an ingenious experiment called the mechanical equivalence of heat that was performed by James Joule. And in this experiment, what he did was he hung a mass around a pulley, and the rope that attached the mass to the pulley was wound around an axle. And the axle was attached to these wooden paddles. And you could crank this crane and you can wind the rope, lifting the mass, and it would turn the paddles. Now, you could lock the handle there and then measure the temperature of the water inside. And this is an insulated container. And then what you can do is you can release the mass. Now, the mass is in the gravitational field. It has a potential energy. That potential energy converts into kinetic energy as it falls and it reaches the ground. While it does that, as it falls down, it unwinds the rope and turns the axle, turning the paddles and churning the water in the calorimeter. And you can actually measure an increase in temperature in the average kinetic energy, the motion of these molecules, that is connected to the mechanical energy that was given off from this mass falling. So a macroscopic energy transfer occurs down to the microscopic states. And this is the whole principle of thermodynamics, where we can imagine the molecules being these hard spheres bouncing around, and their average motion gives rise to things like temperature, eventually pressure, and the idea of volume. Now, if you push down on that too much, you're going to push up against quantum mechanics. But the example that I want to look at is, what if you had this vessel, and in this vessel what you had was cold water on one side and hot water on the other side. Now let's say you had a barrier here that kept all the cold molecules here, water molecules here, and the hot ones there. Now, this is a low entropy state because it's ordered, okay? Over time, if you were to remove this membrane, you would expect that on average, the faster moving hot water molecules would bump into the slower moving cold water molecules. In that collision, they would give them energy, slightly raising their speed, slightly decreasing their speed. And over time, what happens is the whole thing would smooth out and the whole tank would be full of lukewarm water. At that point, you wouldn't be able to tell a direction to time. But up until that point, as you saw the hot water blending in with the cold water, you could see a forward video and a backwards video and tell me which direction time flowed. But again, there is nothing stopping, if you wait long enough, for the water to spontaneously separate itself in this way. And that's because there's some statistical probability of each molecule being anywhere in this volume. Okay, and we're going to do some calculations to show that. So essentially what happens is entropy on a global level always increases. So you have to look at the system as a whole. For example, if you say, look, I go to the store and I buy a beverage and I want to enjoy this beverage cold. I want it cooler than room temperature. Well, if you come home and leave it on the counter, or if you put it in the cupboard, it will remain at room temperature. But if you put it in the refrigerator and wait a little bit, that temperature will cool down until it's at the same temperature as the refrigerator. And you might say, aha, I have now cheated nature because I have made entropy decrease. Okay, the molecules that were moving at a certain velocity, now those velocities have decreased, driving the temperature down, making it into a more orderly system. And if let's say it was water that you wanted cold, you take the water, now you put it in the freezer, right? You wait even longer, the water now thermalizes with the freezer and it freezes, even more highly ordered. And you can say, look at this, I am going against the arrow of time. How am I doing this? Well, if you feel the back of the refrigerator, it's warm. And that's because heat is being pumped out of the cavity of the refrigerator and the cavity of the freezer, and it's being exchanged with the air in the kitchen. So the air in the kitchen, the air is going to get warmer. The kitchen gets warmer at the expense of this. Plus, you have to do physical work. You have to plug in the refrigerator to do that work. If you unplug the refrigerator, it's no different than your cabinet. So then you say, well, look, I have air conditioning, so I can cool down the kitchen. But if you go outside and you touch the air conditioning unit, you're going to feel the hot air being pumped out of the kitchen. And that's going to heat the Earth, right? The Earth is part of the solar system. The solar system is part of the galaxy. Galaxy is part of the cosmos. The whole thing ends up increasing. So you can have local lowerings of entropy if work is done. However, this global idea is what increases always. So let's do a numerical example. So what I want to do is I want to look at a two-sided container, a left side and a right side. And what I'm going to do is I'm going to introduce different numbers of molecules. And in the first experiment, I'm going to have one molecule, and it's a two-sided container. And I'm going to ask the question, what is the chance of finding the molecule on the left-hand side? In each experiment here, I'm going to be peeking inside the left-hand side of the box. And I want to ask the question, what are the chances it'll be there? So if I have one molecule, obviously it can either be on the left side or it can be on the right side. So there are two possible outcomes, but only one of them satisfies my condition of being on the left. So for one molecule in a two-sided container, it has a 1 in 2 chance of it being on the left-hand side. Now, what if I have two molecules and I'm introducing different colors here? So I have a orange one and a green one. Now, if I have two molecules, I now have 4 possible states that the molecules could be in. They either both could be on the left, they either both could be on the right, or they can be some mixed state of one and the other. And again, there's only 1 out of 4 that satisfies the criteria that they're on the left-hand side, so I have a chance of 1 in 4. If I introduce a third molecule, if I introduce a blue molecule now, and I do the same thing, now I have 8 different possibilities, only 1 of which they all are on the left-hand side. So as I introduce more and more molecules, the chances of it being on the left-hand side decrease. Now what I can do is I can increase this to 100 molecules. And the way this trend is going is you take the probability, which is 1/2. You have two cavities, one of those will be occupied. And then it's 1/2 raised to the number of particles that you have. Remember, if you had one particle, you had 1/2 to the 1. Let's go back to that, right? One particle, 1/2 to the 1 is 1/2, right? Two particles, 1/2 to the 2 is 1/4. Three particles, 1/2 to the 3rd is 1/8. So that's how you would get the probabilities. That's how you build the probabilities. So let's say you had 100 molecules. Let's say you had 50 fast-moving molecules on one side and 50 slow-moving molecules on the other, and you want to see the probability of that happening by itself. It would be 1/2 raised to the 100, and that would be one chance in 8 times 10 to the 31st. Okay? Now, let's say that you, and what this means is 80 million trillion trials, or 80 nonillion. That's what that comes out to. So let's assume you can do this experiment and you would do one trial every second. So every second that goes by, you can freeze the experiment and you can tell where each of those molecules are, and you can determine if we're in a state where the slow ones are on one side and all the fast ones are on the other. And if you did it at that rate, you would need an amount of time that's 200 trillion times the age of our universe to see it once. So it's not that it's impossible, it's that it takes so long, we've never seen it. Okay? And this is what drives this arrow of time. Now, if you look at a mole, right, 100 particles is nothing. If you look at thermodynamics, typically you have 6.02 times 10 to the 23rd. This number goes really low. It's not that it will never happen. It's that it takes more time than we've had observation and will ever have observation to observe it. To give you some idea of how big a mole is, if you were to take a mole of pennies and you were to divide them equally to every person on Earth, then every person would be 4 times richer than Jeff Bezos. That's how big a mole is, okay? Now what happens is you get these situations where if enough time goes by, you get what's called a heat death of the universe. You get an expansion due to dark energy. You get black holes absorbing matter. You get super black holes absorbing more matter. And eventually what happens is you're going to get an end to black holes. And the reason why black holes don't live forever is because there's something called Hawking radiation. So if you take it really down to the end state of what will happen to our universe, we know that through E equals mc squared, we have particles coming in and out of existence all the time. And what you're looking at here is a million billion frames per second, or 10 to the 24 frames per second. And this is looking at quarks and gluons interacting on those timescales. If you have particles coming in and out of existence near the event horizon of a black hole, it's possible that one of those virtual particles crosses the threshold while the other one escapes. And when that happens, it costs something for the black hole. It costs energy, and through E equals mc squared, it causes a mass loss. This is the basis of Hawking radiation. So if you wait something like 10 to the 100 years, then all the black holes will eventually evaporate. So the universe that we see today looks something like this. The future universe will look something like that. And this is what we know as the heat death of the universe. So this is the way the world ends, not with a bang, but with a whimper. Heat death. However, here's the thing. Fluctuations. The background is never quite zero. Space-time is full of teeming particles. If you wait long enough, okay, if you wait something like 10 to the 10 to the 56 years, then you will get a fluctuation out of this background where matter is in greater number than antimatter. And it could happen in a particular space-time where the laws of physics permit atoms to form. And then those atoms can evolve into molecules, and then through gravity, sculpt out star systems, planets, humans, and us talking about this right now. Once you get this heat death, you have a space-time So you have time, but you no longer have a direction to time. So in a universe that's in a heat death, you would never know how big it was, and you would never know how old it was. But through these fluctuations, which are allowed through quantum mechanics, through the Heisenberg uncertainty principle, and through E equals mc squared, you can get this happening again. So it could be that we're part of this cycle. It could be that we have not only a multiverse with different detached cosmoses, but actually a single cosmos that goes through this repetitive cycle, and we would never know where we would be. Now, I'm a big fan of the Twilight Zone. So there was an episode called A Penny for Your Thoughts. And I like the old Twilight Zones with Rod Serling. And he starts off always the episode with an introduction. And for A Penny for Your Thoughts, he said, one time in a million, a coin will land on its edge. Well, all it takes is all it takes to knock it over is a vagrant breeze, a vibration, or a slight blow. So kind of this idea of an ordered state going to a disordered state, many different ways I can knock the coin over, very few ways that I can put it on its side. It turns out that it's not quite one in a million. There's actually a paper that you can read where people did this experiment. And if you use an American nickel, which would give you the greatest chance that it's the thickest one that we have, it turns out that in 1 in 6,000 tosses, it will land on its side. So if you make one toss of the nickel and it lands on its side, it's not impossible, but it's very unlikely. But what if you have an infinite number of tosses? What if you have an infinite number of nickels being tossed an infinite number of times? Then this will happen an infinite number of times. The fluctuation that we would see would happen an infinite number of times. And we would be here discussing this an infinite number of times. We would have a situation where a space-time could have laws of physics that could create a periodic table through various astrophysical events. And this direction to time that we talked about, this idea that might have bothered you of when I said that the sandcastle could maybe come up from the background of the flat sand, that actually happens. And in fact, you're the sandcastle. You are the fluctuation. We are this fluctuation that came out of this highly entropic microstates, and then eventually through a cosmic fluctuation, we end up getting this ordered system. And if you think of it that way, the whole universe can be thought of as a beautiful fluctuation. And with that, I'll end, and I'm happy to take questions.
All right. I will set this to allow folks to unmute if you'd like, if you want to ask a question, or you can type it in the chat. So there we go. Should be able to unmute if you'd like. One thing, I'll jump in here. One thing I always found interesting is the concept of negative temperatures in entropy and time. Do you have any thoughts on it?
So in terms of going to absolute zero or
Right.
reaching an absolute scale?
Or the fact that the negative 0 Kelvin is actually hotter than 0 Kelvin, things like that.
Yeah, so the interesting thing about zero, so for those who don't know, the Kelvin scale is the absolute scale. So theoretically, zero should be the limit. Now, there's different ways of arguing why you wouldn't even get there. One way is by working backwards from the analogy that I gave with the refrigerator. The water was at room temperature, you put it in the refrigerator, it cools down to 40 degrees Fahrenheit or whatever you have your refrigerator set at. It won't get colder than that because that's the ambient refrigeration temperature. If you then want it colder, you got to put it in an environment that's colder, that's the freezer. Now, if you start with something that is above absolute zero, you need something eventually colder than absolute zero to bring it down to that zero. So that's one way of looking at how you can't go from this system. Now, what would convince you that you would be in this state? From the fluctuations from quantum mechanics, this non-zero background fluctuation, we could, trying to realize a thermodynamic system that's at absolute zero means that there's no motion to the particles. So those velocities are zero. And if those velocities are zero, that would mean I would absolutely know the position. And there are uncertainty principles in quantum mechanics that limit your combined precision of momentum and velocity, and also energy and time. So from a quantum point of view, you would not expect that system to ever be in an absolute zero. And if you wait long enough, that system that's above can fluctuate. So one of the answers that you can have for why is there something rather than nothing is simply this idea that nothing is unstable. If you wait long enough, you get these fluctuations, and empty space-time is something. It's more of a rearrangement of what's there. One example I give my students is I hold my hand up, and I'll try to do that here so we don't lose my hand. I hold my hand up like this with my fingers stretched out, and then I make a fist. And I ask them, wow, it looks like the fist came out of nothing. Well, the fist didn't come out of nothing. The fist is a rearrangement of the fingers that are there. So you could always rearrange a system in a way that that either makes a low entropy system or a high entropy system. The big question is, why was it so ordered in the first place, right? What made it ordered? And one of the answers you can have is that, again, if you wait long enough, you will get particles, Maxwell's demon, this idea of what are the chances that all the air molecules in the room will find themselves under the desk and you end up suffocating. Well, there's a non-zero chance that that'll happen because those molecules can be anywhere statistically, but it's astronomically improbable. But if you have a space-time that is in heat death, then time is you don't have a way of making a clock. There's no matter there to be able to oscillate. So you have a space-time but no direction to time. You can't measure lengths, you can't measure durations. So it might as well be an instant in that universe from one universe to the next. Other questions? Please feel free to either unmute your mic or type a question. No other questions?
Yeah, looks like folks are going to be shy today. That's fine. All right. Well, thanks a lot, Dr. Stamatikos. That was an excellent talk. And again, I'll remind folks about our talk next month, given by, again, our own Dr. Harmon from Ohio Wesleyan. That, again, is on December 10th and starting at 8 p.m. right here on Zoom. The Zoom link will be posted on the website. And for those folks on the email list, I will send it out in email. So watch out for that. Again, thanks a lot. And have a good evening, folks. I'll leave the Zoom go on for a bit if people have additional questions. They feel like
sure, I can hang out.
So, but this ends the official part of the program. Thanks a lot.